Hello, everyone. Welcome to the first talk of the CAE seminar series in fall. Our speaker is going to be Professor Bowei Li from Texas Tech University. He's an assistant professor there in the Civil, Environmental, and Construction Engineering department. His research interests span machine learning-based meta-modeling, large-scale multi-hazard risk and resilience assessment, AI-powered automated design, maintenance, and decision-making. His group seeks to bridge state-of-the-art AI techniques with computing, designing, and decision-making for large-scale structural and infrastructural systems. He has a PhD in civil engineering, scientific computing, and MSc in electrical and computer engineering from the University of Michigan in 2022. And before that, he has degrees from Tongji University and Hwasong University of Science and Technology. So thank you very much, Dr. Lee, for presenting on efficient performance assessment for large-scale engineering systems under wind hazards, frameworks, and applications. All yours.
Okay, so thank you so much, thank you so much, Prannoy. And it is actually the privilege is mine. And so let me just first share my screen. And okay. Hey, hello everybody. I just confirmed that you can see my screen here.
Yes.
Okay. Hey, hello everybody, and my name is Bowei Li, and I'm currently assistant professor in Texas Tech, although my start date is September 1st. So I hope all of you have a small start of your new semester, quite exciting, but kind of critical sometimes. Okay, so my topic is efficient performance assessment for large-scale engineering system under wind hazard frameworks and applications. Okay. So as we know that especially and you are currently in Miami in Florida and you are aware of that. So almost in every year we see devastating hurricanes. So extreme events like extreme wind events like storms and hurricanes may cause tremendous loss because it has caused tremendous damage to structural and infrastructure systems almost every year. So and I would highlight here. So actually, I really like Florida, and for the first year when I come to the United States, and I spent my road trip in Florida. But when I was driving through somewhere, and I cannot remember the name. So those two photos are what I took. I think it is an area that's struck by hurricane during 2017. So actually, I was truly shocked by that. And so it is pretty important. It is pretty important also to push forward the research to make our built environment safer and more resilient. Okay, so why it is like that? And one of the reasons is that the current wind design practice are still code-based prescriptive procedure. As a result, the performance of the system, structure system, infrastructure system under extreme events are not explicitly known. So as you don't know it, you cannot optimize it. You cannot get it well engineered. So as a result, so there's an unexpected behavior devastating outcomes when there's extreme events. Therefore, there's a strong motivation to move to performance-based wind engineering. Excuse me. So, and here's an illustration for the performance-based wind engineering framework that is given hazard. Excuse me. I think I'm still in the annotating mode. Let me get rid of that. Okay, so given hazard to quantify extreme wind, so we analyze the structure, or infrastructure system together to respond data, and we can go ahead to evaluate the damage, quantify the damage. Then we evaluate the decision variables, for example, loss, for example, the performance, and then we can optimize it, get it well engineered. But for example, regarding hazard, we roughly know when, but we don't know exactly when the next hurricane will come, and we don't know, for example, how intensive it will is. So there's uncertainty associated with the hazard. Also, we have a rough idea about the structure system, but there's still uncertainty because of imperfect knowledge of the system and because of inherent uncertainty as well. All of those uncertainty will propagate through this pipeline and until to the end, making this problem a highly complex probabilistic problem. Okay, so when we are trying to push forward the industrial adoption of this framework, one major barrier is computational demand. And one major source of the computational demand is within the analysis of structured systems, and why it is so time consuming, why it is so computationally demanding. So the first point here is that so our structure and infrastructure systems in practical engineering, it is typically of pretty high dimensionality because we need to ensure the accuracy of our simulation. So it is a large scale, and when in extreme events, it can experience damage. So there's a nonlinearity, and the problem itself is dynamic. So now we have three keywords: large scale, nonlinear, dynamic system, and we need to analyze that. So that leads us to nonlinear dynamic analysis for large scale systems, and we know that it is notoriously time consuming. And what is even worse is that I didn't mention that how we are going to capture the uncertainty. And typically, how we capture that, of course, it is through for example, the simplest one, especially for such a complex problem. So almost the only way is some kind of Monte Carlo simulation, which requires you to repeat this time-consuming process for 1,000, even millions of times to gather the samples. So, and as a result, the whole problem is computationally very challenging. And my research is actually to focus on address the computational demand and push forward the industry adoption of the whole framework. Okay, so now I have a question for all the audiences here. Suppose that you have a car, a pretty old car, that's pretty slow. How are you going to fix that? So, for example, I can just send it to mechanics and try to improve the performance, or I can just discard it and buy a new one. That exactly corresponding to the first two research thrusts that I'm going to talk about here. So the fast response solver is actually try to improve the performance of the existing solver. And the deep learning meta modeling here. So meta model here is exactly meaning that I'm not satisfied with my algorithm, with my model. I find some other meta model to replace it. So the meta model here can ensure the accuracy is 100 or even 1,000 times faster. So the second idea here is forget about the old car, forget about the existing algorithm, and bring in deep learning networks to mapping the input to the output really efficiently. So the last thing here is a little bit interesting. It is a real-time forecast of hurricane-induced damage risk to envelope systems. So the whole idea here is to take advantage of the computational efficiency gain and to see if it is possible that we forecast the hurricane-induced damage for building envelope systems, just like weather forecast. If we can do that, of course, we can take precautions and inform our, for example, the response management. Okay. So I'm going to through the three thrusts one by one. So the first topic, fast response solver, is actually to see how we can improve the existing solver. So typically, the structure system and I'm not sure for graduate students here, have you already learned structured dynamics? If you already learned that, I believe you are kind of familiar with the equation that's shown here. It is actually the equation motion of the structure system. And here you probably note that the resistance force is a nonlinear atom. So actually it is expressed that the system has nonlinearity subjected to external wind excitation, so which is a stochastic precise. Okay, so now typically in practical engineering, the direct integration algorithm is pretty widely used. So it is actually a time step-by-step scheme. So in every time step, we solve for a displacement vector. So, and as we've already mentioned, that structure system, so engineering systems in practical engineering is of pretty high dimensionality. So that means, so the length of the vector that you are going to solve, typically it's the displacement vector of the structure system. So the length of the displacement vector also represents the size, the dimensionality of the problem, that equation that you are going to solve. Can be up to thousands, even millions. So, and we need to solve such a big problem for every single time step. What is even worse is that typically in practical engineering, you know, that the implicit solver is adopted, which means that we need to perform iterations when there's any nonlinearity. That is an addition to the big addition to the computational demand. And so so all of those need to be performed for every single time step. And I didn't mention that how many time steps do we have. So for seismic, it can be like thousands, but for wind, it can be like millions of time steps. Okay, so now we see why it is slow. So first, it is a great number of degrees of freedoms, high dimensionality. Secondly, potential computational demand associated with solving nonlinear equations. Thirdly, so the great number of time steps. Okay, so targeted on the three major sources of the computational demand, we developed the fast response solver. Actually, it is called adaptive fast nonlinear analysis, AFA algorithm. So targeted on the computational demand associated with solving the nonlinear equation. Okay, we introduce adaptiveness in the location of potential nonlinearity, particularly instead of when there's any nonlinearity. Instead of considering the entire structure, which is pretty big, we only focus on those where are nonlinear. So typically, especially for well-designed structures, so the location of nonlinearity is pretty localized. So so to introduce adaptiveness of location of potential nonlinearity can really save a big deal of computational demand. Okay, so the second point here is that adaptiveness in the number of modes or degrees of freedoms. So so actually we can only consider a few number of modes or degrees of freedoms when the structure system is in linear elastic loading, unloading, or unloading or reloading range. Okay, so so regarding the great number of time steps, so we introduce adaptiveness in a time step. Particularly, here's an illustration. So we first proceed with pretty large time steps, since at the beginning the structure system is in linear elastic. So when there's any nonlinearity, okay, so I becomes more cautious and proceed with small time steps, and to consider more number of modes just to capture the nonlinearity, because typically nonlinearity is pretty localized feature, needs high order modes to capture. Okay, but when the structure system go back to linear elastic loading, unloading, or reloading, we can go back to consider a few number of modes and large time steps. Okay, so now we are curious about if the scheme will work or not. And here's the case study that we considered. So it is 37-story steel structure that's modeled in OpenSys, that with a consideration of distributed plasticity with 5 integration points per element. Okay, so it is subject to wind load and including across and along wind case. So it is compared with the direct integration. And here is so here is actually what we have shown here is the efficiency compared by time ellipse. So as we can see for both the crossed and unwound cases, it is almost 10 times efficiency improvement. So it should be noted that here for both the cases, and you are going to see the nonlinearity is extremely high. We should note that the code implementation of our algorithm has not yet been particularly optimized. So in practical engineering, we can expect that there's a 10 times efficiency improvement, an order of magnitude improvement. So, and here is actually the comparison for the response time histories. For the above is the global displacement, and local and below is a local history curves. So as we can see that for both the global displacement and local history curves, so for the entire time history, data obtained by AFA algorithm overlaps perfectly with the direct integration, indicating a pretty high accuracy. And here we can see that at the very end of the time history, so here is a significant residual displacement, meaning that so the nonlinearity of the system is extremely intensive, but the AFA algorithm is capable to ensure the accuracy and with pretty great efficiency as well. So, and it is also impressive to note that in local history curves, so the accuracy is pretty high. So as always, it is pretty hard to ensure pretty hard to ensure the accuracy of the local history curves. Okay, so now the AFA algorithm has already been integrated in the method 3 of performance, method 3 in the pre-standard of performance-based wind design schemes. So so AFA algorithm to offer the response and performance response and structural behavior analysis to offer us with 2 advantages. So the first one is that offers comprehensive response time history and response time history data. So at and beyond the state of shakedown. And secondly, it has an order of magnitude efficiency improvement compared with the direct integration. So we also developed a software. Actually, it's user-friendly user-friendly software just published, and you can scan the QR code here. So if it is of interest to try it. So in short, it is called wind reliability analysis. In short, it is VERA. So it is a software to allow us to implement the method 1 and method 3 in the pre-standard performance-based wind design schemes. Oh, I see that there's a chat here. Okay. Thank you so much for now. Yep. Okay, so I think it is first part. The main takeaway here is that we developed a highly efficient response time history analysis algorithm called AFA algorithm. We integrated it into the method 3 for the pre-standard performance-based wind design schemes for the analysis of the structure, response, and behavior to analyze for the system level reliability of our structured systems, and we developed that into a VERA software, and it has already been published, and you are encouraged to try out. Okay, so go back to the problem that we have, the question that we have at the very beginning. So we asked that actually, if you have an old car and you are not very satisfied with that, so the second idea is that you can just discard it and buy a new one. Okay, so here the second topic is actually corresponding to that. So it is a deep learning meta modeling here. So meta modeling essentially means that we have already talked about that. So suppose that your algorithm, your model is slow. So how about we find other meta model? Actually it is another model called meta model. Sometimes it is also called surrogate model as well. So the surrogate model or meta model is capable to produce results that accurately enough, but it is 10 times, 100 times, even thousands, millions times faster. So, and now we are going to introduce that. Again, so it is our problem. So the structure system can be considered as the equation of motion that we have shown here. So essentially, it is a mapping from, I'm still trying to annotate, excuse me. Essentially, it's trying to mapping the from my input, my excitation to, for example, the stochastic wind load to the response time history that we have. So we've already talked about that in practical engineering. Both the inputs and outputs can have pretty high dimensionality from the perspective of degrees of freedoms and by time steps. Okay, so that means the mapping from the input and output is of pretty high dimensionality. And typically, we solve the problems through nonlinear dynamic analysis, right? So, and now the idea is that, can we just forget about it, find a new one here that is actually, so can we use a deep learning neural network here to finish the mapping from the input to the output? So here the answer is yes, but I should stress here that both the input and output are of pretty high dimensionality. So it can be pretty challenging if you directly bring in deep learning neural networks. So before we consider that, the first idea here, so the first step here is that we consider spatial reduction to reduce the degrees of freedoms that we have. Secondly, we perform temporal reduction to reduce the length of the time series. And after that, so we have inputs and output with reduced size, and we can go ahead to introduce deep learning neural networks to find out the mapping from the inputs to the output with reduced size. Okay, and regarding spatial reduction here we perform projection-based reduction. That is, actually it is rely on a coordinate transformation matrix phi hat here to reduce both the inputs and outputs. So to obtain phi hat, we perform single value decomposition over a snapshot matrices that collecting snapshots of the high fidelity, high dimensional response data of the structure systems. And after the single value decomposition, so the first matrix phi here is actually the coordinate, so is actually the PUD mode matrix. And typically it is fairly enough to just keep the few low order modes. It is enough to ensure a pretty high accuracy transformation and computational computational accuracy. Okay, so now with phi hat, you can project the inputs and outputs, the excitation and the response into a lower dimensional space. And here we should note that both the reduced inputs and outputs are still of the same length of the same length to what the response and the excitation that we have not yet reduced. So the second step here is that to reduce the length of time series. So the idea is to take advantage the wavelet approximation to convert both the reduced inputs and outputs to be a much shorter wavelet coefficient series of my inputs and outputs. Okay, so after that, and we can introduce deep learning neural networks here to find out the mapping from the inputs and outputs of reduced size. Okay. So now we should note that the mapping from the wavelet coefficients of my reduced inputs to the reduced outputs are still a sequence-to-sequence mapping problem. So a type of neural networks that pretty suitable for this task is actually called a long short memory neural network. So here is the schematics of the meta modeling scheme. Okay, so so how are we going to use that? So actually, given the time series of the given the time series of wind excitation, so we first perform the projection with the proper orthogonal decomposition modes that we have to reduce it to the reduced inputs. And then we perform wavelet transformation to transform it to much shorter wavelet coefficients of my reduced inputs. We take this as the input to the long short-term memory neural networks to predict for the wavelet coefficients of my reduced output. After that, we use that to approximate actually the wavelet approximation to approximate my reduced outputs. Okay, and now we can perform superpositioning of our PUD modes to approximate our high fidelity, high dimensional response. Okay, so here is the entire process that we have. And to test the performance, here we consider the pretty high dimensional structure system with the distributed pretty high fidelity nonlinearity subjected to across and along wind. So, and it is compared with the direct integration, and here's the configuration for the training and testing. So after it is calibrated, so we will test it through 200 separate excitation and response data pairs. So here's a comparison for the efficiency once it is calibrated. So here we see that compared with the computational demand with the direct integration, the math model is the time that needed by the math model is negligible. So it is if you compare the numbers, it is actually more than 50,000 times. It is pretty impressive. So and here is actually regarding the accuracy of the math model that we have. So on the on the above is a comparison for the global displacement, and in the below is a comparison for the local hysteretic curves. So in the above, the first feature here, probably it's better that I have a pointer, laser point. Okay, I think that is more helpful. Sorry about that. So in the first feature here is a comparison for a response time history. As we can see that the response time history obtained by the meta model and the direct integration called full model here overlaps. So which means that the accuracy is pretty high. So the error that does not accumulate with time. And at the very end here, so we note that there's a significant residual displacement, meaning that the case is extremely nonlinear, but we are able to ensure the accuracy. And here is a comparison for the peak values of 200 samples in the testing set by the direct integration and the math model that we have. So as we can see, the high accuracy holds for the entire testing site. So it is not surprising to note that the excitation probability curve that based on the peak values that we have is accurate. So below here is a comparison for the local hysteretic curves. As we can see that it's pretty impressive that the high accuracy maintained for the entire time horizon, maintained almost for all the testing sets. So it is always pretty challenging to ensure such a high accuracy for the local hysteretic curves. Okay, and now what we just done is actually to integrate the meta-modeling scheme with stratified sampling scheme to enable efficient estimation of small failure probability. So the stratified sampling scheme is designed actually to sampling for example, the hazard curve, the rare events, and to enable us to evaluate small failure probability without considering too many numbers of samples. And the meta model that we have is designed to accelerate the single analysis for a sample, but the meta-modeling scheme is actually focused on only one intensity level. So now the idea is that by transfer learning, we first calibrate a meta model with respect to the last strata of my hazard curve, and then we can use transfer learning to quickly adapt it to all the rest of strata. So now for all the stratas, we have a meta model to efficiently and accurately reproduce the response samples, as many as response samples that you need. And based on those reproduced response samples, you can quickly calculate the small failure probability. Okay, and here's an illustration with the structure system subjected to set specific wind hazards, and with the directionality of the wind captured by sector scheme. Okay, so here's a comparison for, in the first row is a comparison for the extents probability for all the wind strata. In the second row, it's a comparison for the response data that we have. So the first column is a peak interstellar drift. Second column, residual interstellar drift. Third column is a peak top drift. As we can note that, so actually the accuracy with all the samples are pretty high, and so it is pretty impressive as we can see that we are capable to ensure the accuracy when we are estimating a small failure probability. So how small it is as small as 10 to the power of -5. Okay, so now here it is the end of the second part. So the second part, the main takeaway here is that we developed a highly efficient and accurate deep learning modeling framework to enable accurate and efficient simulation of our response time history of large-scale structure systems. And it is so we tested that was calibrated. It is 50,000 times or more, and we integrated it into with the stratified sampling scheme by transfer learning, and we are able to accurately and efficiently estimate small failure probability, and the probability of this small has already been enough for the response analysis of our structure systems. Okay. So the third part here, actually, we are considering how we can take advantage of the computational gain, such that if we can forecast the damage risk to our building systems, just like weather forecast. Again, given that, of course, it will be a pretty good information for emergency response, for emergency management. Okay. So the framework is composed of 3 parts. So the first part is actually the real-time so the first part is literally a weather forecast. It is actually the real-time forecast that set specific wind speed and direction. And the second part is the high fidelity performance-based multi-domain coupled damage evaluation model. So the third part is Kriegen. It is a kind of meta model to accelerate the simulation. And now I'm going to go through it one by one. Okay. So regarding the forecast of hurricane here, we have the real-time forecast of hurricane track from the National Hurricane Center, and so we take the National Hurricane Center prediction as the mean track, where we consider the uncertainty associated with some prediction error for our tracks. Okay, so and now we can sample. Actually, we can sample tracks from this spatial Gaussian precise. So for a specific point of my sample track, and we can employ a parametric wind field model to evaluate, it enables us to evaluate the field of wind speed and direction. Of course, we can extract the set specific wind speed and direction at the location of my building. And now we can forecast the wind speed and direction. So the next step is that given wind speed and direction, how we can evaluate the damage of our building envelope system. So here I would introduce the damage mechanisms. So the building envelope system can susceptible to damage because of two reasons. First, it is excessive deformation. It is excessive deformation because of interstory drift. So it is drift-induced damage. Secondly, it can be blown away. So it's the pressure-induced damage. Okay, so regarding drift-induced damage, the demand, as indicated by the name, of course, is interstory drift ratio here, which can be solved by solving the structure dynamics. Okay, so for the pressure-induced damage, the demand is equivalent pressure, which requires us to calculate the external wind. So we already have the external wind pressure, and we calculate the internal pressure, and so it is and we can go ahead to evaluate the equivalent pressure here. So it should be noted that the two sources of damage can couple. For example, if there's a specific envelope element has already been damaged by drift, so you will expect it is easier for pressure-induced damage to happen. So that means if drift-induced damage happens, then there will be a reduction to the capacity to the pressure. Okay, so if we stop here, given wind speed and direction, and we will already have all the information to simulate for the envelope damage. So now if we directly do that, so the difficulty for the real-time forecast is that it is way too time consuming. It is computationally demanding again. So now so it comes to the third part, is that we try to accelerate the simulation. It is a Kriging meta modeling here. So the Kriging essentially is a Gaussian process conditioned on the data points that we have. Okay. So once you condition the Gaussian process on the data point, then you will have a predictor here. So the first part of the predictor is actually the weighted regression part to capture the global trend, and the second part is like a radio interpolation to capture the local features that the data have. So once it is calibrated, so the key advantages here first, of course, it's of our interest is efficiency. So it is highly efficient. So there's no matrix inversion, so the nonlinear, and there's no matrix inversion and no need to solve for the optimization as well. So secondly, it is capable to weight the contribution of different data points based on their distance to our new inquiry point. Okay, so now here's the idea. So how we are going to use the framework. Okay, 5 minutes left. Yeah, and I think we're almost there. Okay, so first we have a high fidelity damage model here. So the idea is that we first gather a set of high fidelity data here. So given we can first generate a set of representative sample points of wind speed and direction. Take that as input to evaluate for a set of conditional damage statistics. That is mean and standard deviation of the damage measures. Okay, why conditional? It is conditioned on the wind speed and the direction samples that we have. Okay, so now we will have data pairs of wind speed and the direction to damage statistics. Okay, and the second step is to use Kriging to learn the mapping from my wind speed and direction to the conditional damage statistics. Once it is calibrated, so it can immediately given wind speed and direction, find the conditional damage statistics. Okay, and now it is offline stage. So for online stage, when we observe that there's an imminent hurricane, okay, so we can quickly forecast the wind speed and direction samples at the location of my at the location of my building. Okay, so we take that as input to the Krigan to forecast for the conditional damage statistics and unconditionalize it so we will have damage. So we will immediately have real-time damage risks. That can be information to inform emergency response and management. Okay, so now here to illustrate the application, here's a case study. It is pretty high dimensional system that was assumed actually in Miami. So actually it has 8,100 even-loop elements. We consider 2 levels of drift-induced damage and 1 level of pressure-induced damage, with the capacity to pressure reduced if the drift-induced damage occurs. Okay, and here's an animation that I generated. Suppose that there's an imminent hurricane Irma. Okay, so here is a figure that we visualize the real-time forecast of my hurricane track with the uncertainty coin. Okay, and here is a real-time forecast of my wind speed direction at my building site. On the right-hand side are the 3 maps corresponding to the building envelope system, and the building envelope system, you can unfold it, and you unfold it and you plot it here as a front, right, back, left surfaces, and you can visualize the damage risk corresponding to the 3 sources of damage. Okay, and with that information, if you observe, hey, the damage risk is pretty high, of course we can take precaution, evacuate expensive devices and that kind of stuff to lower the loss and enhance the resilience. Okay, so I think due to the limited time, and I'm going to leave the conclusions here. And I would say that it is my privilege to be invited here to give a talk. And thank you so much for your time. And I will see that currently there are 2 PhD position opening in my new group. And if you are of interest, so in the future we are going to do artificial intelligence and tailoring artificial intelligence for wind and structure engineering, particularly for the simulation of large-scale structure and infrastructure systems, automated design, decision making, for large-scale structure and infrastructure systems. And you are more than welcome to learn more from my personal website as a QR code here, or recommend students. Okay, and thank you so much, and see if there's any questions. And of course, I would acknowledge the whole research effort is with my previous advisor, Dr. Simon Spence. And thank you so much.